we have worked with two experiments. One was related to light traveling from rarer to denser, and another experiment is related to light traveling from denser to rarer. In this experiment, we are going to understand a concept called total internal reflection and the critical angle. Let's try to understand these, and I'll frame some questions for you. Okay. What is meant by reflection? What is meant by total internal reflection? These are concepts will also be addressed. But this finds lot of applications in the real world. So when doctors use the stethoscope, total internal reflection of the sound waves occur. So that is the reason faint heartbeat can be clearly heard in the doctor's ears. And same thing happens to diamonds. The shiny brightness of the diamonds is due to total internal reflection. So in that case, diamonds have very high refractive index because of the total internal reflection is much more easy to occur. In materials like water, the refractive index is less, so total internal reflection will happen, but it will be at a very bigger angles of incidence. Anyway, let's discuss that topic right now. I want to first frame a question. Before that, I want to introduce the concept of total internal reflection. Now imagine this is a surface, the interface as always. I'm not telling you which is the rarer, which is the denser. Let's say light travels from one material to another. So when it hits the interface, two things happen. Bending of light would happen. For now, I'm just drawing it closer to the normal. This thing is called the refraction, as it traveled to the other side. Light bent and traveled to the other side. But some amount of energy will even travel backwards into the same material. So some to the other material, some within the same material. This bounce back of the light energy is called reflection. So it's just reflection. It has nothing to do with total internal reflection. Now let me talk about total internal reflection. If not even a little bit of light energy goes to the other side and everything comes back. Let's say in a new example, there is no refraction and all the light energy that we have supplied is traveling back in reflection. Then we call this total internal reflection. So what is the difference between reflection and total internal reflection? In total internal reflection, nothing goes to the other side. That means this surface behaves like a pure mirror, like a metal coat, and everything comes back. In case of reflection, some energy will travel to the other side, remaining comes back to the same side. So then we call it only reflection and not total internal reflection. That is the concept. Now, here is my question. When do you think there is a possibility of seeing total internal reflection? When light travels from rarer to denser, or when light travels from denser to rarer? When do you think there is a greater chance? Try to recollect our previous experiments and think about this for a second. Now let me reveal the answer. When light travels from rarer to denser, you can observe it always bends towards the normal. Let me pick a different light ray which is of much more greater angle of incidence. In this case, it will bend, but it will again bend towards the normal. So as you can see, in case of rarer to denser, even if I take an angle very close to 90, it will still bend towards the normal. So under such scenario, there is no way light would bounce back to the original side. It might, but total internal is not possible because light is always bending towards the normal and refractions will always occur. So rarer to denser, total internal reflection is not possible. Now look at denser to rarer. In this case, as light travels from denser to rarer, it bends away from normal. Now let me take a wider angle. This time it should bend further away, maybe it travels like this. And one more. Maybe in this scenario, it travels along the interface and a little bit more incident angle might actually make it come backwards in the same material. So this last case, see this particular scenario where this is the incident ray and nothing is going beyond, everything is coming backwards. Okay, this particular scenario corresponds to total internal reflection. So it's very simple. Here it's not possible because light is always going to the other side and coming close to the normal. Here light is going away from the normal. When there is enough push, there is a good chance it might not go to the top and it might come backwards. So denser to rarer scenarios will give us total internal reflection, TIR. Now I want to demonstrate the activity, but before that there is a table. Let's write the table. I have the table on the board. As you can see, this is the incident angles and these will be the refracted angles. We are not going to write reflected angles. And once we complete this table, we are going to learn about critical angle of refraction. So let's go ahead and see the experiment right now. So look at the material. We need the same as before, a semicircular glass slab, our full circle sheet and a laser light. I am going to project light from denser to rarer. This is our interface. On one side we have denser, other side we have air, that is rarer. So let's start from 0 as always. For 0 degrees, the refraction is 0. For 10 degrees, the refraction is 16 or 17 degrees. I am making a note of these values. For 0, I have 0. For 10 degrees, it increases as it is going away from the normal. Now, for 20, observe this, there is refraction, there is no total internal. You can see there is some energy coming back in this direction. This is reflection. You cannot call it total internal reflection as refraction is also happening. So this is 36 degrees. Then for 30 degrees, I am seeing 50. For 40 degrees, I am observing 80. There is reflection, there is refraction. 40, it's 80 degrees. And lastly, for 50 degrees, there is no refraction, as you can see. Nothing is happening over here. Entire energy is coming backwards to 50. It's behaving like a mirror, this entire interface. So that's why angle of incidence is equal to angle of reflection. The same thing happens with 60 degrees also. For 60, you're seeing somewhere very close to 60, no refraction is happening. Now let's get back to the board to understand what just happened. So here is the data that we collected from the topic. Now as you can see, until 40 we saw refraction, that was 86 degrees. And as you already know, when light travels from denser to rarer, it bends away from the normal. That's why we see a bigger angle. Now at 50 degrees, if you remember, there was no refraction. Everything was coming back like hitting a mirror. So that's why I'm not giving an angle over here. I'm just calling it total internal reflection. For 60, it is the same. Now try to understand what just happened. Until 40 degrees, you saw refraction, but at 50 degrees, you did not see refraction. You saw total internal reflection. So try to get this logic. That means between 40 and 50, at some angle, refraction turned to reflection. We need to find the angle at which this change occurred. That particular angle is called critical angle. So one more time, let me recap what I just said. Until 40 degrees, refraction was available. At 50 degrees, total internal reflection happened. That means refraction vanished. So somewhere from 86, we have 90 degrees of refraction. This particular place where refraction happened, that corresponding incident angle where you see 90 degrees is called critical angle. So we are going to use the experiment to find this critical angle. So it's simple. Let me talk about a number line. So observe this. You have a number line. On one side you have negative numbers -3, -2, -1. And another side you have positive numbers +1, +2 and +3. The location where negative is changing to positive or positive is changing to negative is called critical number. For a number line, 0 is the critical number. If you apply the same idea over here, at some critical angle, reflection is changing to refraction or refraction is changing to reflection. That particular critical angle we need to find out. For that, we'll get back to our apparatus to understand where that critical angle is. So here, instead of starting from 0, I'm starting from 30. Please observe, at 30 degrees, the refraction is 50, just like before. Now what I'm doing is I'm not leaving the laser light button. I want to slowly move it away from 30. As I move it away from 30, the incident angle, you can see refracted angle is slowly closing towards 90. As soon as this refracted ray touches the 90 degree mark, I will stop. So I'm moving it further. I'm further moving it, further moving. Now observe, that's where the refracted ray is brushing this surface, or in other words, it is showing 90 degree refraction. And the angle at which this is happening is 43 degrees. One more time. We are starting from 30. I'm slowly moving my laser light without breaking this path. And as soon as the refraction touches the 90 degree line, I will stop. And if I check at what incident angle this change is occurring, it's occurring around 43 degrees. So let's recap carefully. At 43 degrees, refraction is 90. Less than 43 degrees, you see refraction. More than 43 degrees, you see total internal reflection. That means this location, 43 degrees, is the critical location where reflection is changing to refraction, or refraction is changing into total internal reflection. So this is our critical angle. Let's get back to the board now and summarize the whole concept. As you have observed from our experiment, critical angle is 43 degrees. What it indicates is at this 43 degrees, so let me modify my table. So I'll just change this. At 43 degrees, we are seeing a refraction of 90 degrees. Any angle more than 43, like 50, will produce total internal reflection. Any angle less than 43 will produce refraction. So this particular location or the incident angle is called the critical angle of refraction. So that's about this entire experiment. It's a very interesting experiment, and as I told you before, it's used in many instruments including optical fibers. The data or the energy always bounces inside the optical fiber and never escapes outside. This saves the data or that energy, and it can travel through millions and millions of kilometers if the optical fiber is of great quality. Thank you for listening to this.